Hello, I'm Serene Belhadj, and this is my Lab 3 report on the black hole. There are two parts to this lab. In part 1, you must analyze the star's motion to find the net force and estimate the mass of the black hole. In part 2, you must fly around the black hole without crashing on the planet or the black hole by determining what initial velocity the ship must have when it leaves the surface of the planet and using Newton's second law to predict the motion of the planet and your spaceship. Here is a brief preview of the results. Newton's second law states that the force of an object is equal to its mass times its acceleration. In other words, the force is equal to the rate of change of momentum. The law relates to the total interactions between the system and surroundings to the changes in the motion of the system. Newton's law of universal gravitation states that every particle attracts every other particle in the universe with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Some forces have components in both the parallel and perpendicular direction, such as the force of gravity. In that case, the force should be broken down into the parallel and perpendicular components for substitution in the net force equations. Here is my code for part 1. I've inputted the mass of the star to be 2 times 10 to the 30 and delta T. And then I have edited the calculation loop by inputting the initial and final momentum vectors, calculating the star's change in velocity and change in momentum, calculating the derivative form of the net force, calculating the parallel component of the net force, calculating the perpendicular component of the net force, and I've used these equations to calculate the mass of the black hole, and I've inputted these arrows to represent the different forces, and when we run the program, we see that the mass of the black hole is... These are the magnitudes of all the net forces I have found: the net force parallel component and the perpendicular component, and the mass of the black hole is 1.04015 times 10 to the 34, and this mass will be plugged in the second part of the lab. Here is the second part of the lab. I've inputted the mass of the black hole, and I have inputted the initial conditions for the spaceship, calculating the initial velocity. The x component is -5 and the y component is 0.33. In the calculation loop, I've calculated the net force on the planet by inputting the force of gravity on the planet by the black hole, force of gravity on the planet by the spaceship, and the net force of the planet. And here I've calculated the net force on the spaceship by inputting the equations to calculate the force of gravity on the spaceship by the black hole, the force of gravity on the spaceship by the planet, and the net force on the spaceship. And here I've included the position update formula and the velocity update formula. This is the initial velocity for the spaceship to get close enough to the black hole without crashing and still be able to leave the system. The x component was -5 and the y component was 0.33. What is the difference between the net force and its parallel and perpendicular components, and the rate of change of momentum and its parallel and perpendicular components? Mathematically, there isn't a difference as the formulas have been proved to be equivalent. However, the rate of change of momentum can be calculated through observation of the system's position, velocity, and momentum as a function of time. On the other hand, the net force cannot be calculated through observation, but rather knowing the mass of the black hole. What initial velocity would your spaceship need to have in order to enter into some kind of orbit around the black hole? Unfortunately, I was not able to find the initial velocity. However, I think knowing the velocity in which the momentum of the ship is perpendicular to the net force on the ship can help.